And now I call as an attendant with apparently today a speaker's badge, an organizer onto the lantern here. Nick has organized this meeting and he has started, you may know him if you used XChem. He has started studying in Oxford, worked at Diamond and was one of the drivers for the Panda software. And I think he's coming to us with some trouble trips because yes, I think the first slide will show where he is now in Sweden.
Hello. Thank you very much to myself for inviting me. It's not actually true. Helen and I both declared conflicts of interest when inviting ourselves to talk, and Clemens overruled us. So you can blame him. So, yeah. Yes, exactly. I've tried my best to be bubble gummed, so we will see how that goes. I've been asked several times where I am now or how Amsterdam is. So I feel like I have to start by saying that neither. So I'm now in Sweden. I'm starting a research group in Linköping, or have started a research group in Linköping. The advantages of Sweden are, of course, that you get beautiful snow, although at the moment in winter it kind of looks a little bit more like this. And we, of course, have wonderful full daylight days to enjoy them of about, 6 hours of daylight per day. So if you want some very dark days full of snow, come to Sweden. And how's it going? This is Midjourney's interpretation of a young bioinformatics professor, which I think is actually pretty accurate. So that's how it's going. This talk basically starts with an apology. I submitted an abstract that was, I think, quite optimistic, and it turns out running a group actually takes quite a lot of your time. So I want to start with this quote of time management is hard, which is myself. And so most of this talk will in fact be methods rather than results. So for the Americans on Slack, oops, all methods. So let's start. What links everything we've heard so far? Time resolved crystallography, fragment screening, compound development series, serial crystallography for the last couple of days. The answer is, of course, that all involve dealing with multiple related structures. If you take time resolved crystallography, you have a crystal, obviously many crystals. You, for instance, trigger them with a laser, and then as a function of time, you collect data that eventually leads to a series of models, as we've just heard. And of course, you build these models through comparison of the different time points to extract the multiple states, the different states, and then build your models accordingly. Fragment screening by X-ray crystallography, essentially the same thing, although of course it looks very different. First thing we do, sort out the ones that have binding and no binding, and then model ligands. This is basically as close as I get to talking about Panda, so hopefully everyone can infer the entire Panda algorithm from this. And then, as we've heard again, serial crystallography, we have many, many crystals. We merge them into using, the magical data processing, which is done by people smarter than me, of converting these into a series of merged data sets. And then from each of these, you solve a structure. I have a small addiction at the moment to generative AI, so this is the first of many, but this is a scientist being crushed by a pile of data. It's a little bit Atlassian, I quite like it, but basically once you start to combine multiple data sets with multiple models, this becomes a big, big pile of data that is really annoying to wrangle, broadly speaking, with current tools. And I guess, broadly speaking, I'm hoping to make this a little bit easier as things go on. Unfortunately, that's not where it ends. So crystallographic data, as we again know, is an average over space and time. So we have a crystal composed of many different molecules, which are eventually all averaged into a crystallographic structure. And so if we have multiple energy states of our protein, you will end up with a model that must have alternate conformations in it. Now, can I get my own pointer to work? The answer is no. Up in the top right, so if you have multiple energy states with different energy minima, you will have some fraction in each state, and those need to be represented in your model. For protein atoms, this becomes kind of actually quite easy to conceive of, not necessarily easy to actually model, because you can see how the atoms are all connected. And you can kind of say, okay, well, clearly this chain just deviates into two different conformations. It's not particularly hard to understand. And of course, given my other research lines, don't forget B factors. They are always present. They do tell you a lot about the kind of the width of these energy minima that you have. So everybody, please do not forget your B factors. This becomes a little bit trickier when we consider ligand binding, because now we have not only something moving, but actually something appearing and disappearing. So say we have an apostate of our crystal where this blue sphere representation of a protein is in a closed conformation and a few water molecules have been modeled and are floating around. You then have your ligand binding and unbinding, but in the bound state, it opens this little loop, for example, and displaces one of the water molecules, and the other two water molecules shift a tiny bit to accommodate it. As we've heard exactly from the previous talk, when you end up averaging over all of these, you have to have, you end up with an average weighted by the occupancy of the two states, and you end up with data that represents the ensemble of states. And now what we need to do is build a model that reproduces this experimental data, because after all, the only thing that we should be depositing in the PDB is fully refined, high quality structures. That's my hot take. What does this look like in practice? So the problem with that is that unlike the alternate conformer of the protein, where you can trace the atoms, once you start adding multiple things on top of each other, unless you color by state, as I've done here, you end up with basically a soup of atoms that's pretty difficult to interpret visually. And even in this case, it's pretty difficult to validate this model. There is a bar of plop for the person that can give best criticism of this slide. Not you, Elspeth. What's wrong with the slide? No resolution information, no contour information, absolutely no details, not the occupancies of the states. But so it's about 60-40. And basically all you can say from this is that where the atoms of your different states overlap is where you tend to get density. So you have this sulfate up in the top right, which leads to a peak that you can see, but you'll also notice distortions around sulfate. It's not perfect. And that's actually caused by superposed water molecules, and their density kind of changes the shape of that sulfate. You can also see that the peak of density around here is the bits where the density from the phenylalanine adds to the density from that ligand and creates a peak that looks like neither of them, right? So it's a nightmare, but ultimately it actually shows something quite interesting, that in the ground state, the apostate of the crystal, your phenylalanine is here. Either the ligand, of course, moves it or kind of takes advantage of it being momentarily absent. The ligand comes in, switches this conformation of this phenylalanine, actually causing the release of an ethylene glycol, and it cooperatively binds with this sulfate. So actually, it's kind of interesting things going on that ligand binding that we can only get if we actually model these things kind of properly and generate interpretable models that we can deposit in the PDB. That is a relatively simple case. If we take another actually also simple case, we have an apostate that, let's say the bound state in this case represented by an ethylene glycol binding, moves all the waters around, and the resulting model, if you look at it in Coot, really does look like a mess. You have waters that are kind of superimposed on the alternate conformations of your isoleucine. You have the aspartate side chain conformation is switching around again with kind of corresponding water positions in each place. The interactions kind of have to all be correct, and you try and interpret these models, and broadly speaking, it's a mess. They are a nightmare to try and remodel or to kind of interpret or in any way actually interrogate while you're modeling. And even then, this is a relatively simple case. I wanted to have a quick note about actually different types of maps. As we have now said multiple times, as I've probably said about 12 times in this talk, we're always dealing with averages, and the conventional maps that we use do not show very good density for partial occupancy features. So 2FOFC maps and emit maps are both instances of these. The 2FOFC maps that you can use are practically useless for interrogating your partial occupancy models. Again, I've forgotten to put resolution on this slide. I'm sorry, Elspeth. And whenever someone, of course, asks you to generate emit maps, you can do classical emit maps, or of course, the much nicer polder maps. These still only show you what the density in the binding site looks like. They will not show you whether it actually kind of looks like the ligand. It doesn't actually validate the ligand, it validates the density in your binding site. But that said, if you have a good model, you can still convince yourself that the model in the top row actually explains the density pretty well, especially when you then combine that with the event map up in the top right, which shows quite clearly the binding pose of the ligand. And then when you look at the polar emit map, you get very nice kind of, you can see exactly the extra density that's changed between the event map and the polar emit map that shows you where all those kind of superposed waters have actually come in. And those waters were not built so that that emit map kind of matched. Those waters came from an APO structure. But even then, this kind of breaks down for low occupancy ligands. So these are now, so the one in the top row is about 20% occupancy. And even then, the polar emit maps stopped being useful. They basically validate your APO water state at the end of the day. I said I had an addiction. So this becomes even worse once we now have to not only deal with multiple models, multiple data sets, but multiple states in multiple models in multiple data sets. So how do you avoid panicking when you start one of these structure determinations? We heard from Patrick on the first day that during the pandemic, when they were doing all the structure solution, there was a significant slowdown when it actually got around to modeling the data. As I said, I don't have the exciting results I was hoping to present, but I'm going to present the methodology behind this, that we can start to make this a little bit easier for users. The workflow for, I'm going to talk about derivative structure refinement, so that can be practically anything where you have a starting structure and changes are applied to it. With a lot of possibles, this is basically partial occupancy, derivative, ligand, structure solution, any mixture of those that you like. There are a lot of available tools for the first step, which is generating your electron density. So you can run Dimple, PipeDream, XDSApp. Of course, we've also heard just now about Extrapolate, where you can kind of skip this initial refinement step actually and just go straight to electron density analysis. Amplitude analysis. But of course, if you run one of these initial refinement pipelines, you can put it into Panda for electron density analysis. Then you get around to modeling, which for Panda is of course done with Panda Inspect in Qt, or at least it will be when we fix the version that's in CSP4. And then of course you at some point want to refine your structure once you've added your ligand, and then you want to get around to validation. Of course, validation of low occupancy features is a little bit contentious at the moment, but I've assured myself that Oliver will present all of these solutions in his talk later. The bits I'm talking about today, I've cut out Panda like I promised, talking about the stuff we're doing on the initial refinement, the modeling, which actually I'm just going to recap what we've already done, and then the post modeling refinement. The first thing we do in the initial refinement, so the approaches used by Dimple and I believe basically everything else, is you take an input structure and you try to either just purely refine that against your derivative data sets, or to remodel it to fit your derivative data sets. We explicitly do not try to do this. What we say is, okay, you know your APO state, you've done a good job, you've modeled it really well, and to the first approximation, it does not change in your derivative data set. New atoms may be added, things may change, but your APO state, the defined APO state, cannot change. That is an absolute. If something does move and change, that is a new state. So as our strong Bayesian prior, that the new data set contains some fraction of the APO state, and that APO state is basically absolute, up to little wiggles. So we generate a series of a lot of restraints for the APO state, so holding the water molecules, roughly speaking, in the same kind of positions, basically creating a big jelly-like network of restraints. Of course, also between kind of protein atoms, maintaining salt bridges, these kind of things, so that when we refine against a new data set, it doesn't get sucked into potential ligand density. So here, for example, you have an ethylene glycol bound in the binding site of a bromo domain. There's a few waters floating around. But when you then have this fragment screening data set where a ligand has displaced this ethylene glycol, actually driven it further into the binding site, but we'll get to that later. We don't want this ethylene glycol from the apostate to actually get kind of sucked into this, because all we're going to have to do is remodel it later. So that works. That's fairly easy. And then it gets to the modeling stage. So you've run Panda and everything has worked fantastically, because Panda always works perfectly. And you remodel your binding site and you stick your ligand in, you stick your ethylene glycol in that's being shoved into this, further into this pocket down here. You model your waters, you model the side chains that have moved, everything's great. Remodel, remodel. Then fortunately, the stuff I'm working on now is automatically merging these two structures so that you don't have to. This is actually surprisingly hard because it's easy to do naively, but then unfortunately you sometimes end up with structures with 23 sets of conformers, and those do not refine well. So coming up with smart ways to come up with a minimal set of conformers that actually refines is a little bit trickier, but we've been working on it. But at the end of the day, what you end up with is a nice ensemble model with a nice set of labeled conformers that actually kind of work. And then the second one, so after you've done this modeling, you go down to your refinement of your ensemble. I'm gonna actually, how am I doing for time? Perfect. And what we now want to do is hold the atoms in place while our B factors and our occupancy settle. We don't want to take our apostate, stick our ligand in, refine it freely, and all of that hard work holding the apostate is gone because that's moved, and all of our hard work modeling the ligand is gone because they suddenly just kind of drift off and wiggle. What we want to do is hold them in place as another strong Bayesian prior and wait for those occupancies and B factors to settle. And we do this by, as I said, again, basically the same approach. Take our initial set of restraints for the apostate, generate a new set of restraints for the ligand-bound state, add them both together on our ensemble model. And then in the first cycle, reset the B factors of this alt lock region to a reasonable value, as always, let's say 30. Refine the coordinates and the occupancies, allow those to settle. We can refine coordinates because these restraints allow things to move a little bit, but we'll hold them roughly where they are. And then the next step, you allow the B factors and to now vary, do full refinement with structural restraints, again, trying to keep it as still as possible and just allow those values to settle. We also have another thing where you can basically generate a series of models where the starting occupancies are sampled actually from Dirichlet distributions, fairly wide Dirichlet distributions, and those enable you to kind of see how well the refinement converges as well. So that's how we get around the problem of occupancy refinement as well. You can see how much the data actually drives your occupancies to kind of consistent values. And then in the last cycle, we just do the occupancy group. So now we're allowing B factors to change. We've removed those structural restraints and everything. And hopefully your model is settled by then and everything will stay still. So this is the simple remodeling workflow that leads to. Of course, this is incredibly simple. You simply start with your APO dataset, model your APO dataset, do your initial refinement, get your bound dataset, run Panda, model that, automatically merge these, and then run your refinement. That should take you about 20 minutes. Eventually. So pause for laughter. So just to round up, so as I said, there will be a beautiful example of this all working that will be published as part of the proceedings. But I just wanted to finish with some kind of tips about how you should do these things when it eventually comes out. It really helps if your starting model is good. I'm sorry, it's just the case. So go around, model the waters in your binding site, like really look at a few of them, check that they are actually consistent and come up with a decent starting model, including, water solvent models, especially in the areas where you're actually going to be modeling your ligands. Of course, you don't necessarily know that a priori, but once you've, say, run Panda and then you've got two main binding sites, maybe go back, look at your APO model in those sites, improve that against APO datasets, and then rerun the refinement and then do your analysis again. That will save you a lot of time downstream. Of course, then your output models from this initial refinement will have low R-frees and good geometries. That's also good. So that's also, let's just assume that's solved because that's not hard at all. and your model won't have moved, so everything will be fine. And then in the refinement, the starting model, we want an appropriate multi-state model. This, again, like I said, will just be magically done and you won't have to worry about it. And of course, again, the output model from this refinement will have low R3 and everything will be great. Do's and don'ts, as I've said, do carefully model the apostate. Do spend some time like getting a decent model. If you have a crappy model going into this, you're going to get a crappy model coming out. Don't be tempted to remove waters and alternate conformers, which is kind of the stuff that we used to do where we were worried about phase bias, or just we would run MR and MR strips out the waters. We want a full, complete model, including all of the decent waters and probably some rubbish ones. And of course, if you've gone into the effort of modeling alternate conformers, you should also leave them in there. You've already done the hard work. And then the input models for the multi-state refinement. Do model the binding site carefully. If you, again, want a decent model showing all of the interesting stuff that's happening upon ligand binding, you modeled your ligand, look around the ligand at the rest of the binding site, see what has changed in the event map. Be careful, do not overinterpret the density. We've talked about this again in the previous one as well. It's still an unanswered question of how do you make decisions in model building. And I'm sorry, I don't have an answer for that in this talk of decision making in MX. But I do want to say that partial occupancy, you can get high quality models. So what this ligand I have here is 20% occupancy. It still manages to have an RSCC of 0.87 against the electron density. You can generate good low occupancy refined models. It is possible. And so my hope is that eventually we can move beyond simple structures and actually move away from having every single ligand in the PDB being 100%. If you refine your multi-state ensemble and your ligand occupancy comes out as 97%, great. You actually have a 97% ligand, but you did not know that before. You were putting your ligand and being like, oh, it's a nanomolar binder, it'll be 100%. You don't know that. This is science. We should start with a null hypothesis. And even if you see beautiful density in your binding site, your null hypothesis actually is that the ligand didn't bind. Okay, I'm not actually going to suggest that it's not there, but you can't then immediately say 100% bound. We do still need to try and do quantitative crystallography. This program will be implemented as something I've, of course, stupidly named murder, where you will be able to take all your fragment screening data sets, import them, hopefully even run Panda within that, and just generate all these models, and actually not just run one model against one data set, but you can take any set of models and refine them against any set of data sets. So you'll just be able to fire these off and not worry too much about moving the data around. I don't really actually have time to talk about this, so I'm going to skip over this. And I just want to thank the person that filled in the survey with what I think is actually a very apt thing. While these new techniques are evolving fast, there's still a lack of easy-to-use experimental analysis tools for their broader adoption. So this is true for fragment screening, time-resolved everything. Only a small set of expert groups are able to perform these experiments if you're ever able to get Panda installed, and this needs to change. So thank you to that PI, you are absolutely correct. I want to thank my group, who are fantastic. Nick is in the audience. Please direct all future Panda questions to him. But of course, I want to thank all the groups that I guess made me the scientist I am and enabled me to eventually become a PI, especially to the people that gave me the money for where I am now, the KO of A. And yeah, looking forward to many more years of exciting science ahead. Any questions?
Very much.
We finished on time.
We had actually we still have enough time to show that slide, but we'll do it in a benefit of having questions. Any questions from the audience? I think, yeah, we have one in the back.
Thanks, Nick. Ben Bax from Cardiff. Nice talk. Could you lower the symmetry or something like that to sort out different models? So you have one model, like, or if you're in P1, you could do 2 A's and 2 B's, something like that, simple.
That's possible. I don't know if it's necessary though, but I think I know what you're getting at, and I would have to think about it eventually. I think it would eventually boil down to the same thing.
A couple of things on Slack. Apparently the Guardian says it's not that grim in Sweden up north.
Oh, it's fantastic.
was not
Ask
a
me how much
question,
my
that was
childcare is.
But an actual question from James Holton. Can you comment on performance/accuracy of occupancy refinement in Phoenix versus RefMac versus other refinement programs, or are you only working with one of them?
I try to write my code to be as agnostic as possible. So it is fully compatible with Phoenix and RefMac. So it works in the abstract space. And then I have a series of outputters that output RefMac restraints, Phoenix restraints. I'm sorry, global phasing, not yet Buster restraints, but that will happen at some point. As to which one is best, I do not want to say because I have not done the work to be able to actually say. I tend to use RefMac, but that is not actually based on anything. Whenever it comes to doing refinements where I want all of the Phoenix tools, I use Phoenix. So I flip-flop. Maybe at some point I will do a study of which one gives best occupancy refinement, but that has not yet been done.
Okay, any more questions from the audience? I think we saw from both speakers now, from Erica and from you, that the initial idea was looking at pipelines and automation, and then looking at human intervention and really looking at where is the end, and you should check your results. How important is it to actually look at these data and then change parameters or can you just rely on these automatic pipelines?
So the thing I'm aiming for here is to automate everything that can be automated. So the initial refinement, for example, we have you have these initial restraints that you're strong Bayesian prior, and you can actually, I think what we'll ultimately do is we'll run with several values of that, and we will use the tightest restraints possible that don't kind of that don't prevent you from getting a good refinement. Because obviously, if you restrain everything completely rigid, you're not doing refinement, and you'll presumably have bad phases and therefore bad maps. So we do need to allow it to wiggle a bit, but we don't want to allow these things to drift off so far that when we add the ligand and refine them back, that they actually kind of settle in. So we will try and automate as much of that as possible, but we also have to allow that. Refinement can be hard, and you do need some refinement models. Like you spend a lot of time optimizing your refinement parameters sometimes, and those will be, you can have user overrides where you can put in these settings into the program, so you can feed these things through. But the intention is certainly that the only things the users actually should do in this is modeling here and modeling here, and hopefully at some point that will also go away and you won't have to do that anymore. So the real intention here is to automate all of the horrible stuff you have to do for occupancy refinement and interpretations of ensembles when you're manually interpreting electron density. So hopefully that will go away.
Thanks very much, Nick. Is there one more question in the room? Otherwise, I close the session. I think it was very interesting, and I hope you agree with me. It was worth getting out of bed. And thank the speakers. Thank you very much.